So in today's lesson, we're going to continue our conversation about reaction stoichiometry and discuss something referred to as the limiting reagent and how it plays a part in our stoichiometry calculations. So if you haven't viewed the video on basic stoichiometry, then I would suggest that that's probably a better place to start. All right, so here it goes. So students sometimes struggle with the concept of limiting reagent, so I think it might be helpful to start with a situation that you are familiar with, and then we can extend that to chemistry. So think about the most basic reaction to make a grilled cheese sandwich. We can write it out like a chemical reaction equation and balance that out. And so we can say that, well, if I have 2 slices of bread and 1 slice of cheese, I can kind of make one sad grilled cheese sandwich, right? And so I know that the proportions are 2 to 1 to 1, right? And so let's say that I had a bunch of friends over and I was looking to make a bunch of grilled cheese sandwiches, and I saw that I had 12 slices of bread left and 5 slices of cheese. And so I would need to think about, well, what is the maximum amount of grilled cheese, or number of grilled cheese sandwiches that I can make given the amount of reactants that I have and the proportions in which they react. Well, in your head, you're probably thinking, well, if I use up all of my cheese, and then that means that I'm going to need 10 slices of bread, and I have at least that. And so the max number of grilled cheese sandwiches is 5. Now, another way to think about that would be thinking about it from the opposite perspective, which is, well, let's just say that I use up all of my bread, then I would be using all 12 slices. How much cheese would I need? Well, given on my 2 to 1 ratio, I would need 6 slices of cheese, but I don't have that. And so I can only make a maximum of 5 grilled cheese sandwiches. And so what that does, what that's saying is that in essence, my cheese is limiting the amount of product that I can form. And so in any chemical reaction, there's likely, unless you have exact proportions, there's likely to be one of your or more of your reactants that is limiting the amount of product that you can make. And that specific reactant, it has a name. It is called the limiting reagent or reactant. Okay, and so let's extend that now to talk about a chemical reaction. And so when I look at a chemical reaction, it's really not too different than that grilled cheese sandwich because, I've written it out as a reaction equation, and we know that the coefficients in the balanced chemical equation can be interpreted to mean moles. So as long as I'm looking at mole values, I can kind of see this in the same way as my grilled cheese sandwich. And so unlike previous stoichiometry problems, in this case, we would be given quantities of 2 or more reactants, and we'd have to make a decision about which of those reactants is our limiting reagent, because of course our limiting reagent is what we use to determine how much product we can make. In the same way that we couldn't really use those 12 slices of bread in the last example to help us predict how many grilled cheese sandwiches we could make. We would be overestimating. So in questions such as this, where you are given an amount from more than one simple reactant, you have to first determine which of those reactants is the limiting reagent. Okay, and so this is kind of how it goes. It's the same way as the way that we thought about that grilled cheese sandwich. So when I look at the number of moles of sulfur, I have 4 moles. And I also know that for every 1 mole of sulfur I need to use 2 moles of copper. So my question to you is, well, if I use up all of my sulfur, how much copper am I going to need? How many moles of copper? And so I've tried to make this question with some nice friendly numbers. Since I know that for every 1 mole of sulfur, I'm consuming 2 moles of copper, if I have 4 moles of sulfur, I'm going to need twice that. I'm going to need 8 moles of copper. And of course, I don't have that much. I only have 6 moles. So in this case, my copper is the limiting reagent because I don't have enough of it to react my sulfur fully. Okay, so in light of that, I would say that my sulfur is the excess reagent. Okay, I have leftover of it. So let's take a minute to also look at sort of like the converse situation. Okay, so let's say instead I decided to focus on copper instead of sulfur. And I looked at this situation and I said, well, I have 6 moles of copper and there's a 2-to-1 relationship between copper and sulfur. That means that I'm going to need to have 2 moles of sulfur, right? Sorry, 3 moles, I should say. Half as much, right? Because it's a 2-to-1 ratio. So then I say, well, do I have 3 moles? Yeah, I have more than enough. And so I'm going to have an excess of sulfur. And so that's why we call sulfur the excess reagent. Okay, so now I think with that preamble, we're ready to kind of start a problem. And I want us to think back about the ideas around that grilled cheese sandwich when we're going through and trying to make sense of this next stoichiometry problem. Okay, so there are 2 parts to this question, but let's read through the whole thing. So this example reads, if 8.5 grams of methane and 15.9 grams of oxygen gas are combusted, what mass of carbon dioxide is produced and what mass of excess remains? So in this part, I'm going to first start by addressing question A. And since there's no reaction equation given, a good place to start, generally speaking, I would say would be to write out a reaction equation. And then you can balance that from there. So I'm reacting methane gas and I'm reacting oxygen gas. And it says that there is a combustion reaction. So I know that in all combustion reactions, the products of complete combustion are carbon dioxide and water. Okay, so that, combustion, that's always a good one to have a handle on because it comes up frequently in chemistry. And so I see right away that this is not balanced. And so I'm going to go ahead and I'm going to balance it. So I'm going to change my number of hydrogens to 4 rather on both sides. And that changes my oxygen count to 4 on the product side. So I'm going to need to add a 2 here and there it's balanced. So, regardless of what you do next, you should start with a skeleton equation and then you should balance that skeleton equation. The next thing I like to do is I like to write out the quantities of each reactant that I have. And you'll know, again, that this is a limiting reagent question because you will have quantities in some measurement or another for more than a single reactant. Okay, and so here I go. And so that's always your first step. You want to make sure that you write out your equation and that you balance it. And again, this is my preference, but write out those measurements, the quantities that you have close by. Okay, so we did balance. We're good with that. Just remembering that we need to do that, putting a 2 here and a 2 here. Now, we know, now that we've done that, I want to talk about what makes sense to do next, right? And so when we had our conversation about basic stoichiometry, we realized that we can't really use these ratios in the balanced chemical equation to mean grams. So we can only kind of work in moles because every atom has its own molecular mass. And so our next approach is going to be to take these mass values and convert them into moles, because then we can use the proportions in the balanced chemical equation to help us relate products and reactants and determine the limiting reactant. Okay, so that's done. We're going to convert to moles. Okay, so we're going to convert all of the species that we have mass values for into moles. And I'm going to remember that, the number of moles of a species are equal to its mass in grams divided by its molar mass in grams per mole. And so I'm going to do that for my methane. And I'm going to go ahead and do this for my oxygen. And so 8.5 grams divided by the molar mass of methane, adding up the mass of carbon and 4 hydrogens, gives me a molar mass of 16.04 grams per mole from my periodic table. And then that's going to give me a value to 2 significant digits. I've got 2 values here, so 2 significant digits. Gives me 0.53 moles. Doing the same thing for oxygen, I'm of course going to take my 15.9 grams, divide that by the molar mass of O2, which would be 32.00 grams per mole. Okay, and so working that out, and I can see here that that 15.9 grams tells me that my significant digit should be 3. And so I am going to get 0.497 moles. Okay. Now, just my preference, but I will often go ahead and I will take those values and write them right below in the balanced chemical reaction, just so I have that sort of isolated and easy to find. Okay, next step. Now, so far things have been, I think, pretty much status quo. We would normally, I think, intuitively know to convert grams to moles, but the next step is a bit new. So let's tackle it. So when we looked at the case of the grilled cheese sandwich, when we were figuring out how many grilled cheese sandwiches we could make, what we did was we said, well, if I use up all of one reactant, how much of the other do I need, right? So for instance, with 5 slices of cheese, how many slices of bread do I need? Well, I need 10. And how many do I have? Well, I have 12 slices, so I have enough. That's kind of how you go about thinking about which reactant is your limiting reagent when we're looking at a chemistry problem as well. So normally I wouldn't normally go through both of these sides of the situation, but I think for this first example, it may be useful for us to see what it looks like depending on what choice you make. So ask yourself, if all of one reactant reacts, how much of the other do I need, right? So I can either do that from the perspective of methane, how much methane is needed if all the O2 reacts, or how much oxygen is needed if all the methane reacts, right? So I need to look at it, I can look at it from either perspective, and if you're solving a problem, you need to make one choice or the other, not both, but I'm going to illustrate what it looks like from either side. Okay, so this is what I do. I'm going to use mole ratios to figure that out, okay? So I know that I have 0.497 moles of O2, right? And so if it all reacts, then I can figure out how many moles of methane I would need, right? And I know that, my balanced chemical equation tells me I'm using 1 mole of methane for every 2 moles of oxygen that get used. Now, mentally, I can kind of look at that and see how that works and why that makes sense, right? I just kind of look at, well, I need half as much methane as I do oxygen. But let's just go through the calculations so that we have a system when the numbers aren't as obvious or aren't as friendly. So 0.497 times 1 divided by 2, okay, half as much to 3 significant digits is going to give me 0.285 moles. And keep in mind, let's look at the cancellation here. I've canceled out moles of O2, and this is giving me moles of CH4, and those are moles that are needed, okay? If I want to react all of my O2, I need this many moles of CH4. So let's go up and see, well, how many moles of CH4, of methane, do I actually have? I have 0.53. So I have more than enough. So I tend to write that out. I like to kind of write that out. I have 0.53 moles, which is enough. Right? I have more than enough. I'm going to have leftovers. So what that tells me is that CH4 is my excess. And by default, that means that my oxygen is my limiting reagent. So that's what that would look like in this case. Let's look at the counter situation. So I may just as easily have said, well, what happens if I use up all of my methane? how much of my oxygen am I going to need? So let's take a look at that. Well, I know that I have 0.53 moles of methane available, right? So if I use all of that, 0.53 moles of methane, how much oxygen will I need? Well, I know that I use 2 moles of oxygen for every 1 mole of methane that I use, right? And so I can see my units canceling here. And so that I could just do the quick math here and kind of see that that's going to give me, my raw value would be 1.06 moles of O2 needed, right? I know that that really should be 1.1 moles, right? And so I'm going to say, well, if I use up all of my methane, the 0.53 moles that I have, I'm going to need 1.06 moles of oxygen. Do I have enough? No. Okay. I only have, I'm going to write that out. I have 0.497 moles of O2. Okay, which is, by the way, not enough. So that's what's telling me that I don't have enough of it. And so if I had more, I could make more product, but I don't have enough oxygen to fully react all of my methane. So that confirms for me that, oxygen is my limiting reagent. Okay, so we've gone through that exercise, and of course that took a lot more time than it would normally if you had done a series of practices. You would sort of just pick one of these options and go with it. But it's important for now for us to know what to do next, right? So we've established that methane is our excess and oxygen is our limiting reagent. But what do we do next? And this is one of the most common pitfalls that I see students kind of fall into when they're working through these problems, is they forget to think logically about the problem. In the same way that with the grilled cheese sandwich, we would never have used those 12 slices of bread to predict how much product. We would never have used the excess reagent to predict how much product. We need to use the limiting reagent, the number of moles of limiting reagent, to help us predict how much product we're forming. Okay, so don't forget, we've just determined that our limiting reagent is O2, and that we would have leftover methane. We're not going to use the methane to predict how much carbon dioxide should be produced. That would give us an overestimate. So let's take a look at that, and that I'm going to call step 4. Okay, so here we go. So now the question says we're going to use the moles of limiting reagent to determine the moles of desired product. At this point, now that we've figured out that oxygen is our limiting reagent, we can kind of just sort of ignore this part right here, ignore it, right? And so I'm going to use the moles of my limiting reagent to predict how much product. Let's do it. Okay, so I know that I have 0.497 moles of O2, but I don't want moles of O2. I want to know, well, what is the corresponding proportional amount of CO2? So I'm going to cancel out my moles of O2. And I know that I have 2 moles of O2 used for every 1 mole of CO2 that is produced. And so doing the math on this, these numbers should look pretty familiar because we would have done this in the previous step. You'll find, like, if the mole ratios are the same, in a couple of different calculations, the values will be the same because we're not converting to grams, so the individual molecular masses don't really matter. And so I'm getting to 3 significant digits, again, 0.249 moles. And so there I go. And so 0.249, I should say 0.248, just rounding because the next digit is a 5. So that should actually be an 8. And so now that I know that I have that many moles of carbon dioxide, I can go ahead and convert that to grams as was requested in the problem. So my mass of CO2 is going to be the number of moles of CO2 times the molar mass of CO2. And so I have 0.248 moles times the molar mass of CO2, which is, 1 carbon and 2 oxygens should give us a mass of 44.01 grams per mole. And looking at the significant digits here, I've got 3 sig figs and 4. So I'm going to truncate my raw value to 3 significant digits. My raw value is 10.936 blah blah blah. So I'm going to truncate that to 10.9 grams of CO2. Okay, and so yeah, so we've figured out the moles, and we've converted into mass values. So we pretty much have answered part A. So part A we have done. The next thing we need to do is look at part B. And so I want to go back for a moment for us to think about the grilled cheese sandwich situation and how we can kind of relate that to help us understand the stoichiometry in this case. Okay, so here we are. So determining excess. So let's just think logically about this. When I look at the grilled cheese sandwich situation, you'll remember initially I said we had 12 slices of bread and 5 slices of cheese. And we determined that I can make a maximum of 5 grilled cheese sandwich with those, given the proportions in that recipe. And so if I really wanted to know, well, since my cheese is my limiting reagent and my bread is my excess in this situation, a question you might get in stoichiometry is, well, how much excess remains, right? And so, well, how would I think about that in terms of the grilled cheese sandwich? Well, I would look at the amount of excess reagent that you start with, okay? So in this particular case, I started with 12 slices of bread. And then I had to use proportions to help me say, well, if I used up all of my cheese, how much bread would I actually use? And so, that amount would be 10, right? I've got a 1 to 2 relationship. And so the amount of excess that was actually used was 10 slices of bread. And so the leftover, the excess remaining, would be the difference between those two. So I would have 2 slices of bread. And I mean, that's not hard to kind of wrap your head around, I think. But somehow when we transfer that to moles, things can get a little muddied up. But I want you to remember this example to help you kind of make sense of the situation and think logically about it. So let's just flip this to the example that we have with our methane. Okay, and I've preserved all the information up here so that we can navigate that. So let's do that. So from the previous calculation, I know that my methane is the excess reagent, and I know how much of it I actually have to start with. So that's pretty straightforward. I have 0.53 moles to begin with, right? And so the amount of excess that you used up, you're going to have to sort of figure out. And so you may have already done the calculation. Sometimes you act sort of just serendipitously, it kind of comes out in the wash, but I'm going to go through that process. So I know that I'm going to be using all of my limiting reagent. All of these 0.497 moles of O2 are going to be reacted. And so if I figure out how much methane will react with it, that will tell me how much of the excess that I used up in the reaction. So I'm going to go ahead and do that. So I have 0.497 moles of O2, and I'm using up 1 mole of methane for every 2 moles of oxygen that I use up. And so that's going to give me 0.497 divided by 2 is, again, we're going to see that's a similar number as we've seen before, 0.248 moles, right? So what that's telling me is that that's how much I actually used up. So I used up 0.248 moles, right? And so let me get rid of some of this down here. And so the difference between those two values will give me my moles of excess. Okay, so the difference between those. And I'm going to round that to 2 significant digits, remembering that my sig figs, my decimals, can't be any more than the value of the fewest. So that's giving me a value of 0.28 moles and that's leftover. And of course, if the question asks, you can certainly convert that into a mass value, and you're pretty much done, and that's it. All right, so hopefully that was reasonable for you to work through. I know it's a bit sticky. I'll post another video with an alternate example of limiting reagent that will help you navigate it, although I won't be going through all of the details that I did here. So this hopefully will at least get you started into knowing how to think through a limiting reagent problem in grade 11 chemistry.